Now we dive into our final main rule, which is going to help us for composite functions. So we're going to learn about the chain rule. So suppose we want to differentiate the function h of x equals the square root of 1 plus x squared. We really can't apply anything we know, at least not just yet. But what we can recognize is that h is a composite function. So basically we have this square root and then we have this polynomial. So if I let f of x be that square root function, g of x be 1 plus x squared, then this function h can be written as the square root evaluated at 1 plus x squared. And on their own, we know how to work with this function. We know how to work with this function. We can differentiate both separately. So we're going to utilize that process to help us actually find out what the derivative of this composite function will be. So this is what the chain rule tells us. If g is differentiable at x, f is differentiable at the output of g, then ultimately my composite function is differentiable at that x value as well. Its derivative is a little bit more complicated. So I've got that composite function. What we actually do is work from the outside in. So I'm going to differentiate the outer function. I do not touch the inside at all, but my chain reaction is going to have me pop the derivative of the inside out as well. So this is the process we're going to follow. In terms of the Leibniz notation, if y is a function of u is then a function of g, and they're both differentiable, then ultimately, if I want to take the derivative of y with respect to x, I got to go through my first variable, and then I go through that second. Okay. So I'm going to do one example just kind of with this process, and you might have some of those like tutor structured questions in your homework about this, but I want to go through and find So I want to go through an example where I'm going to go through this process using these two functions, defining f, defining g, finding each separately, and then plugging into this formula. Realistically, that's going to be way too tedious to actually do though, so we're going to keep this process of dealing with an outer and an inner function, and so we'll see how to combat that very soon. So pretty much we're going to find the derivative of the function we started with. So this is a composite function. I can write it as f evaluated at g, where g is that inside function of 1 plus x squared. The outer function, I'm going to change the variable to be the square root of u. I need to differentiate both of these. So if I differentiate the outer function, we bring that power down because it's square root, so 1/2 power. Decrease the power by 1. So the derivative of my outer function is 1 over 2 root u. And the derivative of my inner function is going to be 2x. So if I want the derivative of h of x, this tells me my derivative, h prime of x, is going to be the derivative of my outer, evaluated at my inner, multiplied by the derivative of my inner. So essentially, we are going to evaluate this derivative at g of x. So that's going to be evaluated at 1 plus x squared. And then we want to times by the derivative of g of x, which is 2x. So if I plug 1 plus x squared into this function, all that does is put a 1 plus x squared here. So this becomes 1 divided by 2 square root of 1 plus x squared multiplied by 2x. And those 2's just cancel. Ultimately, the derivative of this composite function is x divided by 1 plus x squared. Okay. So writing everything is tedious. Writing each separate function, writing the derivative of each function. Really what you want to keep in mind is you're working from the outside in. So we differentiate the outer function, but we keep it evaluated at the inner function. Then we multiply by the derivative of the inner function. So I'm going to show you a quicker process in all of these next few examples. So I want to start by differentiating my outer. And I'm going to get used to that Leibniz notation because we are going to use it very soon. If I want to find my derivative, I'm taking the derivative with respect to x of cosine of x squared plus 2x. So I'm going to label all of my pieces. My outer function is this cosine function. My inner function is this x squared plus 2x. So what chain rule tells me is I take the derivative of my outer, derivative of cosine is negative sine. So that's the derivative of the outer. This stays evaluated at the inner function, which is x squared plus 2x. So it stays evaluated at the inner. And now my chain rule reaction is I go ahead and multiply by the derivative of the inner. And the derivative of the inner would be 2x plus 2. So this is where it's pretty useful that you put more steps than you need. But for simplicity, I'm going to skip that. Okay. Let's try another one. Let's do sine to the fourth of x, which remember is really the sine function raised to the fourth power. So if I want to find this derivative with respect to x, I'm taking the derivative of sine of x to the fourth power. So this is a little bit harder. My outer function is that fourth power. So it's really like we have x to the fourth is the outer function. The inner is going to be sine of x. So if I differentiate the outer function, that would be 4x cubed. So it'd be 4x cubed. But it has to stay evaluated at the inner. So I still need to keep that process. This whole thing is the derivative of the outer, but it is evaluated at the inner. And then my chain reaction tells us we have to multiply by the derivative of the inner. The derivative of the sine function is the cosine function. Okay. So ultimately, our derivative, y prime, would be 4 sine cubed of x times cosine of x. All right, so this gives us an even more general idea. This outer function was really a power function. So the outer was something to a power. If we have that, our composite function basically then is a function to a power, where g itself is differentiable. So when you're differentiating the outer function, combining that with the power and chain rule ultimately tells you to take the derivative, you bring that power down, You decrease the power by 1. G of x still stays on the inside. And the only new thing we have to add is chain rule tells us we have to take the derivative of the inside as well. Okay? So this is really the main idea. That's all there is for chain rule. And it's just going to take practice and take as much practice as you need. Do as many extra problems as you want. I'm going to do about 4 more of these. And then you want to get ample practice on your own. Okay? So now I'm going to go in and I'm going to show more detail. I'm not going to sit here and dissect what's inner, what's outer. Let's start with the function 2x to the 5th plus 7x to the 4th, all raised to the 7th power. So applying our chain rule, we bring that power down. We decrease the power by 1. So this would now be the 6th power. And chain rule tells us we have to take the derivative of the inner. So this is where I'm adding those more steps, which I want you to get in the habit of as well. So taking that derivative would give us, bring the 5 down to give us 10, x to the 4th. Bringing the 4 down gives us 28 x cubed. And you can definitely leave it like that. Do not try to multiply this out. Okay. Let's try another one. Let's try 1 over the 5th root of tangent of x. Remember, 5th root is a 1/5 power. So this is ultimately just tangent of x to the negative 1/5. That outer function is the power. So we go ahead, bring the power down. We decrease the power by 1. So that would be negative 6/5. We do not touch the inside at all. But our chain rule tells us we need to take the derivative of the inside as well. Okay. Derivative of tangent is secant squared. So we have negative 1 over 5. Tangent to the negative 6/5 would put that 6/5 in the bottom. So it'd be tangent of x to the 6/5 times derivative of tangent is secant squared. So if you want to make this a nice single fraction, that's negative secant squared of x over 5 tangent of x to the 6/5. Okay. All right, got 2 more for you. Work with a long one. We've got a function inside of a function here, a function inside of a function, and we are multiplying these two. So we need to use product and chain rule for this problem. So I'm going to start. I've got my first operation, or that main operation, being this product. So before I take derivatives, I want to write out what it would look like using product rule. So our derivative will be the first function, cosine of x plus sine of x to the 3rd. And then we want to multiply by the derivative of 3x to the 4th plus 1 to the 10th. Okay. Now we want to differentiate the first piece. So I'm really going to copy and paste this. And my derivative location changes. So I take the derivative of the first one, which I'm going to have to use chain rule for. So going through these, my first piece does not change. Derivative of 3x to the 4th plus 1 to the 10th. Applying chain rule, we bring the power down, decrease the power by 1 to give us the 9th. Chain rule now tells us we have to take the derivative of the inside. So again, going to not jump into it, just say I need to take this derivative of the inside. Now for our second piece, I've got to differentiate this fun function, which again, the outer is the power. So we bring the power down, decrease the power by 1. So we'll get cosine plus sine to the second, multiplied by the derivative of the inside. So we need to take the derivative of cosine of x plus sine of x. And then we keep this 3x to the 4th plus 1 to the 10th. Okay. So we've still got 2 more derivatives that we have to take before I have the actual derivative. So rewriting everything, this is cosine of x plus sine of x to the 3rd times 10 3x to the 4th plus 1 to the 9th. And the derivative of 3x to the 4th would be 12x cubed. Derivative of 1 is 0. For the second piece, we need to take the derivative of cosine plus sine. That becomes negative sine plus cosine. And then times this last piece. Okay. So if you left it here, that's perfectly fine. I'll do one more piece because I can multiply these 2 quantities, and I'm going to put them out front. So that would be 120x cubed times cosine of x plus sine of x to the 3rd times 3x to the 4th plus 1 to the 9th. And then this second piece really can't do a whole lot of. Okay. You can simplify it further. You can take out some of these cosine plus sine squareds. You can take out some quantity of the 3x to the 4th, but this is perfectly fine to leave here. Okay. So I've got one last example, which is going to be a real doozy. We've got the square root of 1 plus the square root of tangent of 8x. So this is going to be like a triple chain rule problem. So kind of thinking about each of these pieces, square root is 1/2 power. So this is the same thing as 1 . So rewriting this first, if I look at the inside, that's 1 plus the square root of tangent of 8x. So square root can be written as a 1/2 power. Then we have this square root on the outside, so it's really like this whole thing is to the 1/2 power. So remember, I've got to go outside in. The outermost thing is this 1/2 power. So when I take the derivative, we bring the power down, decrease it by 1 to give us negative 1/2. The inside stays completely untouched. Okay. But our chain rule tells us we've got to pop out the derivative of the inside. So we need to multiply by the derivative of 1 plus tangent of 8x to the 1/2. That's our first chain rule within here. Okay. So to clean this up, you can move that negative 1/2 in the bottom, and it would become 1 over the square root of 1 plus the square root of tangent of 8x. Just rearranging it. Now I've got to take the derivative of this thing. Luckily, derivative of 1 is 0. When I move on to go through the derivative of this, I have, again, a function and a function. So I go outer in. The outer is this 1/2 power. So we bring the power down. We decrease it by 1, so we get tangent of 8x to the negative 1/2. And another chain rule tells us we go ahead and take the derivative of the inside. So we need to take the derivative of tangent of 8x. Okay. Cleaning this up now, we've got a 2 and a 2 in the bottom, so we could rewrite that at this moment. I'll save that until the next step though, because I'll just rewrite this second piece. This is 1 over 2 square root of tangent of 8x. Okay. Now I need to take this derivative. Again, working from the outer in, my outer is my tangent function. Its derivative would be secant squared. We do not touch the inside at all, but chain rule tells us we have to multiply by the derivative of the inside because it's not just secant of x. So I've got one more derivative to take. Okay. But I can combine these first two pieces. 2 times 2 would give us 4. And then I've got 2 square roots in the bottom. So I've got the square root of tangent of 8x and the square root of 1 plus the square root of tangent of 8x. And then that's multiplied by secant squared of 8x. The derivative of 8x would be 8. So we do have some simplification. 8 over 4 would give us 2. So in the most simplified form, this is 2 secant squared of 8x divided by the square root of tangent of 8x times the square root of 1 plus the square root of tangent of 8x. So chain rule, inside chain rule, inside chain rule. Okay. All right, so definitely get lots of practice with this section. You want to be really comfortable with chain rule. Now we can do tons of new functions, chain rules, product rules, quotient rules. Combine all those together. Got power rule in there too, all of your trig functions. So you can get some really messy derivatives. So take the time, write the steps, use as much as you need. Don't worry about taking up space.